sometimes it's very handy to have an old DOS computer, a Toshiba, and you know something of BASIC, and that's a very easy to learn programming language, and put all kinds of interesting formulas in a BASIC program. Of course, nowadays we live in 2019 and it is not necessary any longer, perhaps because all these formulas, etc., are available on internet. But anyway, it's interesting, and this is only a small demonstration to calculate the resonance frequency. Here it is on Wikipedia. This tells something, but doesn't give any insight, in my opinion. Anyway, let's do some calculations. And I've made the formula in such a way that I can calculate on the basis of the inductance in microhenry and the parallel capacitor. So, inductance, parallel capacitor, and that gives us insight. Say we have an inductance of 100 microhenry and a capacitor of 500 picofarad, then the resonance frequency is 712 kilohertz. And you can do the calculation anew. So let's say we take now 200 microhenry and again 500 picofarad. We see that the frequency goes down to 503 kilohertz. But it's more interesting perhaps to see the effect of the parallel capacitor. So when this is a variable capacitor, when you have here a variable capacitor, there you can see when you have a fixed coil of, say, let's take a fixed coil of 200 microhenry. That's approximately 50 windings, 60, 70 windings on a PVC tube of 1 centimeter diameter, and a variable capacitor between, say, 50 picofarad and 150 picofarad, and then we are approximately 450 picofarad or 500. And let's see what the effect is of that variable capacitor. So, calculating again, we take 200 microhenry. The capacitor has a bandwidth of 50 picofarad to 450, so start with 50 picofarad. And the frequency is 1.5 megahertz. That's medium wave. So let's see what happens when we take here 500 picofarad. So we have, in fact, then the well-known coil, and then that these two plates, one stator, one rotor, you can turn them opposite to each other, and this is connected. I have to hold the camera with one hand, so sorry for this bad writing, but I hope you know how a variable capacitor looks like. The first was 50 picofarad and now we go to 500 picofarad. So again 200 microhenry, 500 picofarad, and now we are on the low side of the medium wave band. 503 kilohertz goes a little in the direction of long wave. So this is a very easy way when you mount this formula into a basic program. To get a good insight, you can get an indication about the capacitor that you need in a certain situation. And let me give another example. Say we have a coil for shortwave for approximately 8 megahertz. Then we need approximately 8 windings. And it is approximately, say, 2 microhenry. It's a guess, but let's say, or it is 5 microhenry for shortwave. And we take a capacitor of 50 picofarad, tuning capacitor, exactly the same circuit. Now we are on 10 megahertz. That's indeed shortwave. This is not a big coil, approximately 8 windings or 7 windings. And let's see what happens when we turn that variable capacitor to the lowest value, to say 1 picofarad. So again, 5 microhenry, 1 picofarad, and now we are more or less out of range. We are on 71 megahertz. That's far too high. Okay, let's do the calculation again. Say we have again 5 microhenry and a 300 picofarad. No, yes, 300. Then we are on 4 megahertz. But we know, for instance, of such a circuit, when the inductance value is small and the capacitive value is high, the bandwidth has another shape. This has a broader bandwidth, and we can also try to get to 4.1 megahertz and try to get a sharp bandwidth. In that case, we have to take more turns in the coil and a smaller value parallel capacitor. So let's take here, for instance, 50 microhenry and say 10 picofarads. 50 microhenry, 10 picofarad. And now we are on 7.1 megahertz in the shortwave band, and we have a coil with a better bandwidth. Of course, that also depends on how the coil was made, the quality factor of the coil. That's also important. But it shows how much you can learn from such a simple calculation. So let's see, for instance, the effect of the tuning capacitor on shortwave. We have again a coil on shortwave of 10 microhenry. That's not much. That is, say, approximately 8 windings. And a 10 picofarad capacitor, parallel capacitor. We are now on 15 megahertz. So let's see what happens when we make this capacitor smaller. How quickly the frequency goes up. So again, 10 microhenry and 5 picofarad. 10 microhenry, 5 picofarad. The preceding value was 10. And you can see now that we suddenly are on 22.5 megahertz. So there is an enormous difference. While we tune that cap only in a very tiny way, we tune that tuning capacitor, you will see that there is a very big frequency difference. And you can compare it, for instance, and this is approximately a real size. This is, for instance, a capacitor, a tuning capacitor on real size, say this is 5 centimeters here and 5 centimeters here, and the distance in between is 1 millimeter, then we have a capacitor of approximately, say, 10 picofarad. And that means that when we turn one of these plates with that small coil, there is an enormous frequency difference. That also means that when we turn such a plate, it will be impossible, more or less impossible, to tune in on a radio station with this resonance frequency. Say we have this in a VFO, variable frequency oscillator, with such a capacitor and that coil, it will be very difficult to catch a radio station, because every small movement while tuning will mean that there is a big frequency difference. So we go very quickly along the different radio stations, and they are, say, they are AM stations, and they are then in that case, say, 7 kilohertz wide. It will almost be impossible to tune in very precisely, and that means that in such a case, when you want to make a radio in this frequency band, you need a tiny capacitor with a very small capacitive variation. Let's see how this program looks like. As far as I know, it is control break, and then we do list, back, list, and that's the listing of the program. And you can see that it is very easy to make only a few lines, and you can of course get all kinds of other programs useful for electronics in such a program. Okay, run. Again, say 200 microhenry, that's the medium wave, approximately 500 picofarad, 503 kilohertz. Now we go back to the main menu, and here are, it is in Dutch, but anyway, you can also calculate, for instance, the inductance of a 1-layer air coil. Also in a formula. The diameter in inches, say it is 1 inch. The total amount of windings, say it is 10 windings. The amount of windings at 1 inch in the length, say it is 10. That means that there is air spacing in between. And now we have made a coil of 1.7 microhenry. And having noted this on a piece of paper, you can go to the resonance frequency formula, this formula, and then do the calculation, and you have an insight in how the coil has to look and for what frequency it is usable. Here, for instance, other Wien-Robinson bridge parallel T filter with their formulas. I don't know. I want to say that I don't know exactly how to put this in a basic program. Of course, I have to study that, these formulas, what all these figures stand for. But when you know that, it's easy to put such a formula into a basic program. Well, that was all.